Picture this. Some of the rarest minerals on Earth are hiding in plain sight across the United States beneath sagebrush in Utah, tucked into a shuttered New Jersey mine, and glittering out of a California hillside. We're talking crystals so scarce that for every fine piece, there can be tens of thousands of diamonds, stones that ignite into electric color under UV light, and one that literally formed when a meteor slammed into the desert. There's even an ore that fooled gold miners for years because it didn't look like gold at all. Before we dive in, take a guess which state do you think secretly hosts the rarest mineral on this list? And if you could hold just one of these in your hand, would you pick the spaceborne spark, the neon glow mystery, or the fire-red desert gem? Here's the plan. We're taking a fast, state-by-state road trip through America's strangest underground treasures. We'll step into Utah's Wawa Mountains to meet red beryl, a gem so uncommon that collectors whisper about it like a myth. We'll climb a dusty ridge in California for benitoite, a sky blue crystal that fluoresces electric blue and forms razor-sharp triangles like sci-fi snowflakes. We'll kill the lights in Franklin, New Jersey to watch a rare trio hardystonite, esperite, and clinohedrite ignite in violet, lemon yellow, and orange under UV. We'll walk the rim of an Arizona impact crater where natural moissanite, a true silicon carbide born from cosmic violence, hides in tiny flashes. We'll duck into Maine's pegmatites to meet pollucite, a rare cesium mineral that underpins some of the most precise tech on Earth. And in Colorado, we'll unmask calaverite, the gold telluride that tricked entire camps until the day someone roasted the worthless rock and watched it bleed gold. Along the way, you'll get the story behind each mineral why it's so rare, the freak recipe of heat, pressure, chemistry, and time that creates it, and the human moments that make these discoveries unforgettable. The prospector who couldn't believe his blue crystals weren't sapphire. The night a mine glowed like a neon reef, the quiet thrill of holding something formed in a split second of impact that changed a landscape forever. Keep a mental leaderboard as we go. Which one shocks you most, and which state's story sticks with you? Ready? First stop, a sunburned ridge in Utah, where a 1 in a million geologic recipe bakes a red crystal so scarce it might as well be phenakite. You see it glitter in your palm. The Wawa Mountains don't shout, they shimmer. Heat ripples off pale rhyolite and juniper shadows. And then, if you're lucky, you catch it, a pin flash of raspberry red from a hairline crack in the rock. Most crystals are smaller than a fingernail, stubby hexagons tucked into gas bubbles and seams inside ancient volcanic glass. This is red beryl, once nicknamed Bixbyt, a name retired because it kept getting confused with Bixbyt. Nothing else in American deserts feels quite this improbable. The recipe almost never happens. Start with a silica-rich rhyolite, already laced with a whisper of beryllium. Heat it, fracture it, and let mineral-charged vapors thread through at just the right temperature and pressure. Then, crucially, add manganese and keep the chemistry balanced so it locks in as Mn3+ inside the beryl structure, turning the crystal a saturated red instead of pink or colorless. Change any one variable, the fluid's path, the oxygen level, the cooling rate, and you get nothing. That's why this place is legend. Up close, the crystals look like tiny stop signs, hexagonal prisms with sharp faces, sometimes transparent enough to read a word beneath. Sometimes silky with microscopic inclusions that make the color glow from within. You'll see topaz, bixbyite, and hematite nearby, but the red is always the star. Collectors talk in hushed ratios because faceable pieces are vanishingly scarce. People imagine gems as glamorous. Here, they're stubborn, often locked in rock, and they reward only patience and sharp eyes. There's a quiet poetry to the setting, too. Wind, emptiness, the crunch of rhyolite under boots, and the knowledge that almost all gem-quality red beryl ever cut comes from a patchwork of claims. Right here, it's a paradox. A desert of wide horizons producing one of the most tightly bounded treasures on Earth. Think about that balance of chance and precision. How many near misses nature endured before landing this exact shade of red. If you stumbled on two crystals in this dust, one tiny and flawlessly transparent, the other bigger but a little cloudy, which would you keep as your forever pocket piece? Go with perfection in miniature or character in size. That trade-off says a lot about how we value rarity, and it's the kind of dilemma red beryl forces in seconds. Now hold that thought. because our next stop flips the palette from desert red to ocean sky blue that not only dazzles in daylight, but explodes under ultraviolet, like a secret signal. Night falls on a dusty ridge in San Benito County, and suddenly the hillside looks like it's sending signals. You sweep a shortwave UV lamp across pale seams of naturalite, and triangles flare to life electric blue crisp edges, here and gone as you move. In daylight, benitoite hides in a clean white matrix with black needles of neptunite. At night, it shouts. The crystal habit is unmistakable once you've seen it. Sharp, triangular faces that seem engineered rather than grown. You can spot a dozen lookalikes in the gem world, but nothing else pairs this sky blue color, this geometry, and this glow. How does a place learn to make triangles out of light? Start with subducted ocean crust cooked into blue schist, fracture it, and flood it with low-temperature fluids rich in barium and titanium. Those fluids thread through naturalite veins, and if the temperature and chemistry land in just the right window, Ba, T, and silicate link into Batc 309 benitoite. If the fluids are off by a hair, you get more naturalite. If pressure shifts, you get neptunite instead, those glossy black prisms that crowd the vein. The triangle is rare because the recipe is fussy and the kitchen is tiny. One narrow district in the California Coast Ranges that nailed the conditions and almost nowhere else on Earth. There's a story here that feels very human. In 1907, a prospector named James Couch went looking for mercury ore and instead found blue crystals he thought were sapphire. When the stones reached a Berkeley geologist, George Louderback, he realized it wasn't sapphire at all, it was something completely new, a barium-titanium silicate no one had ever described. He named it for this county, and in time, California claimed it as a state gem. Even then, the legend grew more from scarcity than size. Most benitoite crystals are thumbnail small, crisp as origami, with dispersion that throws rainbow fire like a tiny torch when cut. If you dig here long enough, you learn the hillside's language. Fresh breaks in the naturalite flash, a hint of blue at the edges. A triangular imprint, just a ghost where a crystal once sat, can be almost as exciting as a crystal still in place, because it tells you you're in the right vein. The best hunters switch between patience and play, scanning slowly by day for geometry and by night for that UV glow that makes decision-making easy. The moment you see a perfect triangular face wink from the white matrix, it's like the rock taps you on the shoulder and says, "You got me." Here's a little dilemma to chew on. If you could only bring one tool to this ridge, would you choose a good chisel and swear by daylight geometry, or a UV lamp and trust the night? Your answer says a lot about whether you'd rather read rocks by shape or by light. Either way, keep the lamp handy, because our next stop is a place where darkness isn't a challenge, it's the whole show. We're heading to New Jersey, where a quiet mine turns into a neon reef when the lights go out. The first rule of Franklin and Sterling Hill is simple: turn off the lights. In daylight, these New Jersey marbles look like ordinary gray-white rock with odd black grains. Kill the room lights, sweep a shortwave UV across a cut face, and the stone erupts. Violet islands bloom where hardystonite sits. Neon lemon streaks of esperite race through, and clinohedrite flares a warm orange like embers fanned by breath. It doesn't feel like geology. It feels like a signal you were never meant to see. You understand immediately why collectors call this district the capital of fluorescent minerals. What had to happen for one hillside to make a rainbow out of stone? Start with a very old seafloor deposit rich in zinc, iron, and manganese. Bury it deep and cook it hard during a mountain building event until limestone turns to marble and the chemistry gets weird in a good way. Zinc and manganese don't just sit still. They migrate into new silicates as the rock recrystallizes. Add a pinch of lead here, a touch of calcium there, and you get a tiny cast of characters that almost never show up together. Hiddenite, esperite, clinohedrite, alongside famous neighbors like willemite and calcite. The glow is the giveaway. Under shortwave UV, trace activators inside each mineral kick electrons up an energy ladder and drop them back down as color. Different lattice, different activator, different light, so one chunk of rock can paint 3 colors at once. There's an industrial footnote that makes this place even cooler. Once UV lamps became field tools, or sorters could literally read the rock in the dark. Bright green willemite meant zinc. Red calcite meant waste. In museums and mine tunnels today, the demo goes the other way. Guides douse the lights, and walls ignite like coral reefs. Hardystonite's purple tends to sit in gentle patches. Clinohedrite usually rims or fills fractured zones with orange. And esperite slashes through in lemon-yellow veins so bright they look painted on. True tricolor pieces where all three crowd together are rare and prized. Little time capsules of the district's wild chemistry. If you ever hold a tricolor specimen, there's a fun choice to wrestle with. Do you display it for daylight's a subtle gray-white marble with handsome more textures? Or build a tiny dark corner so that, with one switch, it becomes a private aurora? It's the same rock, two personalities, and which one you choose says a lot about whether you value mystery or clarity. And here's a small puzzle to mull over. If you could add a fourth glow to this lineup, what color would make the perfect balanced cool blue to calm the heat, or fierce green to push it over the top? Pack the lamp. We're trading neon caves for open sky. Next stop is Arizona, where a cosmic collision forged a mineral so tough it became a lab-grown rival to diamond. But here, in nature, it hides as tiny, improbable sparks in the crater's debris. Stand on the rim of a desert bowl so big it swallows sound. Wind skims the lip of Arizona's Barringer. Crater meteor, crater and every stone underfoot is part of a story that took less than a second to write. Somewhere in this debris field locked inside the shattered iron of the Canyon Diablo meteorite is a mineral that almost shouldn't exist on Earth at all. Moissanite, silicon carbide, tough enough to spar with diamond, and usually known only from labs. Here, it's natural and tiny, born in space and delivered by violence. Why is it so rare? Earth's surface is an ocean of oxygen, and silicon carbide hates oxygen. Expose sick to our atmosphere, and it oxidizes away. Bury it deep in most crustal settings, and it dissolves into other minerals. Meteorites are different. They're little reducing worlds forged in carbon-rich, oxygen pore pockets of the early solar system, where silicon and carbon can bond and survive the trip. When the Canyon Diablo body slammed into this plateau some 50,000 years ago, it scattered nickel, iron metal, stishovite-riddled sands, and inside some fragments microscopic crystals of moissanite. If you slice and polish the right meteorite shard, you might catch a speck that throws hard white pinfire back at your eye. There's a human twist to the tale. In 1893, a French chemist named Henri Moissan studied Canyon Diablo fragments and found minute crystals he first thought were diamond. Years of testing later, he realized they were something else entirely, silicon carbide in nature. The name moissanite stuck, and the irony is, delicious today, most moissanite you see in jewelry is grown in a lab. While the natural stuff that made the name famous hides as dust, fine grains in a handful of places, this crater included. It's the ultimate mismatch between fame and footprint. Walk the rim, and you can read the impact in textures. Shattered limestone welded into breccia, rusted lumps of iron that survived the fireball, glassy splash that cooled mid-flight. The moissanite is too small to pluck from the dirt by eye, but knowing it's here changes the way the landscape feels. You're not just looking at a hole. You're standing on a boundary where chemistry from space met geology from Earth, and for an instant made something both stubborn and beautiful. That's the rarest trick of all. Not just a mineral, but a meeting of worlds. Here's a choice to chew on. If you could take home one memento from this place, would you pick a palm-sized piece of crater wall that tells the story in scars? Or a sand-grained fleck of meteorite that hides a single cosmic crystal you'll never see without a microscope? Big story you can touch, or tiny truth you have to believe. Which one feels rarer to you? Pack your curiosity. We're heading from cosmic chemistry to cold New England pegmatites, where a pale, blocky mineral with an unromantic look quietly powers some of the most precise tech on Earth. Cold air, spruce resin, and the crisp ping of steel on feldspar. Welcome to the pegmatites of western Maine. Out here, the granite swells into pale walls and blocky veins, and pockets crack open like eggs if you choose the line right. Everyone dreams of neon tourmaline and glass-clear quartz, but the real prize for our list is strangely plain. Chunky, chalk-white masses that feel heavier than they look. At first glance, you'd walk past them. At second glance, your hand lingers. This is pollucite, a cesium-rich aluminosilicate from the most evolved part of these LCT lithium cesium tantalum pegmatites, one of the rarest industrial minerals the US produces in any quantity, and a quiet backbone of precision technology. Pegmatites are granite's last sigh, a syrupy residue loaded with water, boron, fluorine, and oddball elements that don't fit into ordinary crystals. As a magma body cools, the common stuff quartz, feldspar, mica locks up first. The leftovers get weirder and richer, concentrating lithium, tantalum, beryllium, and, if the chemistry is perfect, cesium, deep in the pegmatite's core zone, where fluids slow and cavities stay hot just long enough. Cesium finds an elegant trap in pollucite. Think of it as a molecular hotel that only admits CS+ and a few select friends. Miss the temperature window, lose the water, or tweak the aluminum to silicon ratio, and the hotel never gets built. That's why, even in a famous district near Mount Mica, have yet the big, clean masses are scarce and celebrated. In the hand, pollucite is all understatement. Massive, off-white to gray, sometimes with a faint greasy sheen on a fresh break. It doesn't flash, it convinces. Tap the pieces together and you hear a denser note than quartz. Put a thumb-sized chunk in your palm and your brain files a quiet surprise. Heavier than expected. Under the loupe, you rarely see tidy crystals, more often a granular mosaic. Sometimes veined by albite, sometimes freckled with tiny tourmaline or lepidolite mica that betrays the pocket's chemistry. It's not a jeweler's darling, it's a refinery's dream. Roast and leach, and you free the cesium. The element with a melting point just shy of a warm day and a reputation for dramatic reactions with water tamed here, bottled in stone. Here's the twist that always lands. Cesium, from minerals like pollucite, sets the heartbeat of time. The official second is defined by the oscillation of cesium-133 and the world's GPS telecom networks. And financial systems lean on that metronome. So this unflashy block from a Maine hillside quietly sinks the planet. Cesium format, Brinson, other child of pollucite steady drill bits, under the North Sea, photoelectric cells, ion engines, specialized vacuum tubes. The list stretches further than you'd guess from a rock that looks like a chunk of sidewalk. There's a human story in these woods too. Weekend diggers who whoop at a streak of watermelon tourmaline sometimes go silent at a pale boulder. Then grin, the slow grin of someone who knows they've found the rare stuff. Quarry owners remember pockets where a gray, unassuming mass turned out to be hundreds of pounds of pollucite worth, more to science and industry than any rainbow crystal around it. It's the opposite of showy, and maybe that's the charm. If you could display just one piece from Maine on your shelf, would you choose a flashy tourmaline that steals every glance? Or a humble pollucite with a secret superpower time itself ticking inside its story? Pack away the chisels and the coffee thermos. We're trading New England restraint for Rocky Mountain mischief. Our next stop is a Colorado camp where gold hid in plain sight bonded to tellurium in a mineral so deceptive that miners tossed fortunes on the dump until someone roasted the worthless rock and watched it bleed gold. High country air and the squeak of boots on frost. Colorado gold country looks exactly like the place where shiny nuggets should leap from quartz. But the rocks that bankrolled entire towns didn't sparkle. They looked wrong. In the dumps around Cripple Creek and the San Juans, miners tossed pale. Brassy blades and granular streaks that wouldn't show a whisper of color in the pan. Only later did the camp wise up. This worthless stuff was calaverite gold telluride, aught to gold, tied up with tellurium so tightly that you couldn't see the metal at all until heat or chemistry set it free. Tellurides are the tricksters of epithermal veins. Picture hot, alkaline, volatile, rich fluids rising from an igneous center. Threading through shattered breccia and fine fractures, drop the temperature and tweak the chemistry. Toward tellurium, and instead of native gold, you get a suite of rare companions: calaverite, sylvanite, krennerite. Calaverite often shows as thin striated blades or granular films hugging quartz and fluorite, a pale yellow-white metallic that tarnishes and hides in plain sight. Pan it, and you'll get nothing. Roast it, and the tellurium oxidizes off, leaving a porous, dark gold skeleton. Switch to cyanide processing, a game-changing move in the 1890s, and suddenly, the same rock that fooled you pays like a dream. The stories from these camps read like parables. A crew swears a vein is barren because the ore won't show color. Someone tosses a chunk into a stove or a test furnace, and by morning the surface blooms with beads of native gold. Assayers become oracles. The paper slip beats the naked eye. In Cripple Creek especially, that shift trusting process over appearance turned a stubborn district into a legend. Even the names feel like winks. A Colorado town called Telluride, a mineral named for Rarest County in California. Fortunes made on a metal most miners never saw until the very end. Up close, calaverite rewards patience. Fresh breaks show faint striations on thin plates, sometimes arranged like fallen cards in a vein. Under a loop, you'll spot intergrowths with quartz and tiny pyrite cubes. With sylvanite around, chevron-twinned blades form V-shapes sharp enough to slice a shadow. It's heavy for its size, soft enough to scratch with a knife, and stubbornly anonymous until you give it the right treatment. That tension between what the eye wants and what the rock is makes it one of the great teaching minerals in American mining history. Here's a thought experiment for everyone who's ever swung a pick. If your last bucket of the day showed zero color in the pan, but the assay red rich in tellurides, would you bet your next week on that vein? Trust the fire in chemistry, or trust your gut and move on? Drop your tick because this is the classic prospector's dilemma, and Calavera still asks it. Shake the soot off your gloves, relieving gold's disguise for the Pacific Northwest, where an alpine granite at a windy pass grows pastel crystals of a lithium zirconium silicate, so rare it barely has a stage to stand on. One more bend in the road, and we'll meet a mineral most collectors have only read about and fewer have ever seen. Wind scours a high pass in Washington's North Cascades, and the granite here looks bleached by altitude pell slabs speckled with black amphibole, rust-orange feldspar, and glossy dark green needles of a gibrin. Tuck into the lee of a boulder and crack a seam, and a quiet color shows itself a soft blush. Not quite pink, not quite peach. Blocky, sharp-edged, glassy faces wink from a pale matrix. This is zektzerite lithium zodium zirconium silicate from the Golden Horn batholith near Washington Pass. A mineral so picky about how it forms that, for most collectors, it exists as a rumor before it exists as a crystal. To grow it, the mountain needed a magma with the chemistry turned inside out. Most granites are balanced. This one was peralkaline overloaded with alkalis. Compared to aluminum, so the oddball elements stayed loose in the melt as the magma cooled and sweated out fluids rich in fluorine and chlorine. The leftovers concentrated lithium, sodium, and zirconium. In the hand, zektzerite reads like understatement. Crystals are usually thumbnail-sized or smaller stout tablets or short prisms with crisp faces, often etched or slightly frosted by late fluids. The color sits in the pastel range, pale tan, peach, delicate pink, sometimes nearly colorless. Fresh surfaces have a vitreous shine. Older ones take on a silky matte that catches light without throwing it. Under a loupe, you might see perithitic feldspar twinning nearby, black sprays of arfvedsonite or stout adron lances framing the pocket, and, if you're lucky, a raspberry-toned udolite grain lingering at the edgia, reminder that you're in one. Of the few places on Earth where zirconium plays in technicolor, the setting forces a different kind of patience. This isn't a mine with benches and levels. It's talus and road cuts, freeze-thaw scars, and seams that hide 2 feet from boot paths seen by 1,000 hikers who never knew. You pop a seam, blot sweat with your sleeve in the thin air, and study a mosaic of pale minerals that all look almost then the pastel slips into focus. A better collector once said that Washington Pass rewards people who can see quiet things. Zektzerite is exactly that, a quiet thing that whispers rare only after you learn its voice. Why does it matter? Because rarity isn't always neon. Sometimes it's the mineral that refuses to grow unless chemistry, temperature, pressure, and time all shake hands in a single square foot of mountain. Zektzerite may never headline a jewelry case, but it carries a signature, a whole magmatic story distilled into one soft-colored shard. If you could hike out with either a palm-sized photogenic crystal of something common or a thumbnail of zektzerite that only a few thousand people on Earth can recognize at a glance, which victory would feel bigger in your pack? Catch your breath-hour trail drops from alpine pastel to Piedmont green. Next, we head to North Carolina, where a chromium-kissed spodumene once fooled everyone into calling it emerald, and a tiny town earned a name from the gem that made it famous. Piedmont heat, red clay underfoot, and a creek whispering through sycamores, North Carolina, doesn't brag about its gemstones. But every now and then, a hillside flashes a green that stops you mid-stride. In a quartz pocket, a slender crystal lies on its side, pale olive from one angle, deep forest from another. Twist it, and the color swings like a traffic light. This isn't emerald. It's hiddenite, chromium-rich, spodumene, the green cousin to kunzite, rare enough that a whole town took its name from the mineral instead of the other way around. Hiddenite feels like a prank on first-time finders because it checks the wrong boxes. The structure is Lialc-206 spodumene with Cr3+, and sometimes a pinch of vanadium, sneaking into a lumencite and painting the lattice green. The color isn't static. It's famously pleochroic, shifting from yellow-green to saturated emerald green as you rotate the crystal relative to the light. Cutters obsess over that because orientation can mean the difference between a sleepy stone and one that looks lit from within. The catch, spodumene has perfect cleavage, which is a polite way of saying it loves to split where you least expect it. Faceable hiddenite is rare, not just because the crystals are scarce, but because getting a clean, lively gem out of one is like diffusing a tiny, beautiful booby trap. How did it get here? Start with lithium-bearing pegmatites, intruding the Piedmont's metamorphic rocks. Add a local source of chromium in the neighborhood certain. Ultramafic bodies and metamorphic fluids can carry a tan. Let those fluids tweak the chemistry along fractures and pockets as the pegmatite cools. In some lucky seams near Stony Point, the recipe landed perfectly, and green spodumene grew, sometimes alongside beryl. Yes, real emerald, quartz, albite, and mica. That's why the confusion ran wild in the early days. Both emerald and hiddenite can pop up within shouting distance of each other, and green is green until you look closely. There's a human thread woven through the glint. In the 1880s, a mineral man named William Earl Hidden came south famously on a mission tied to Thomas Edison's search for suitable metals, poked around in these hills, and sent specimens to a chemist, J. Lawrence Smith. Smith took one look, ran the tests, and realized this wasn't beryl at all. He described it as a new variety of spodumene and named it after Hidden. The town soon adopted the name too, and the legend stuck. A place where emerald might be emerald, or might be something rarer that only reveals itself when you turn it in the light. In the hand, hiddenite is all angles and restraint. Crystals tend to be slender, striated, prisms with glassy faces, and that chameleon green that deepens when you find the right axis. Under daylight, the best pieces glow, cool, and clean. Under warm indoor bulbs, they tip toward a grassy yellow-green. A loop shows faint growth lines and the occasional veil-teeny feathered inclusions that are both character and caution sign for anyone thinking to buy a saw. Most collectors, once bitten by a cleaved crystal, become poets of patience. The smartest cutters spend hours just deciding how a stone should sit on a dopstick. Here's the decision that divides every finder at the creek. Say you pull a 3-inch crystal with killer color, but a whisper of a fracture near the middle. Do you gamble him for one perfect high-risk cut that could yield a once-in-a-lifetime gem, or keep the crystal whole as a specimen? A natural time capsule you can turn in your fingers and watch the green shift with the sun. Heart versus head, beauty versus certainty. One last detour remains on our map of final rarity that brings the whole trip full circle with a surprise hiding in plain sight. Thin air, loose scree, and a sky so close it feels like you could touch it. Welcome to Colorado's high peaks, where aquamarine hunters climb for blue and sometimes come down with something colorless that's rarer. You crack open a myrolitic pocket on Mount Antero or Mount White and fish out a glass, clear, crystal sharp, lustrous, and at first glance, just another piece of quartz. But the faces are crisper. The heft feels a hair different. And under a loop, the geometry doesn't quite match the hexagons you expect. This is the surprise hiding in plain sight. Phenakite, B2CO4. A beryllium orthosilicate whose name comes from the Greek for deceiver because it has tricked generations of eyes. Why does it hide so well? Phenakite grows in the same late-stage cavities that feed smoky quartz, topaz, and beryl. You need a highly fractionated, fluorine-rich granite pegmatite that kept a whisper of water and volatiles to the end and just enough beryllium, left over to build something other than beryl. In those gas-charged pockets, as temperatures slip and the chemistry narrows, beryllium locks into an orthosilicate lattice instead of the ring structure of beryl. Miss the timing, and the bee goes elsewhere. Lose the fluorine, and the pocket never opens. Cool too quickly, and the crystals stay stunted or never form at all. That fussy recipe, plus beryllium's natural scarcity, is why clean, Well-formed phenakite is scarce, even in famous districts. In the hand, the differences start to sing. Quartz usually shows hexagonal prisms with pyramidal terminations. Phenakite tends to grow as blocky, short prisms, rhombohedral to trigonal in habit, with flat mirror-bright faces that meet at slightly off angles to a quartz-trained eye. The luster is glassy, but somehow harder. The edges feel crisper, and the fracture planes, when they do show, break with a conchoidal snap that still looks too perfect. On the hardness scale, phenakite runs 7.5 to 8 enough to just edge past quartzsand. Its refractive index sits higher, which is why cut stones can throw surprisingly lively flashes for something that looks so plain in the rough. Mount Antero crystals can be near water, clear, or tinged with smoke, often perched against microcline and albite, side by side with aquamarine needles that make every pocket feel like a tiny sky. There's a human beat to this mountain lesson. Plenty of US seasoned collectors included have bagged nice quartz only to find later, under a loupe or on a refractometer, that the best quartz in the tray isn't quartz at all. The phenakite grin shows up right after the realization. You were fooled, but you were fooled into rare. Old-timers will tell you that Antero rewards the patient eye more than the strong back. The folks who learn to see small differences walk away with the best stories. The punchline is lyrical to our road trip began with beryllium's loudest burst of color in Utah's red beryl. And it ends with beryllium-S quiet phantom, a colorless crystal that hides by looking ordinary and wins by being anything but. Here's the final nudge for your brain. Set a phenakite and a quartz prism on a table at arm's length. No labels, no tools. Which tiny clues would you trust to call the deceiver? Face angles, luster, the way the light skates across a flat. Or would you admit that sometimes the smartest move is to bring it home and test, because humility finds more rare minerals than confidence ever will? Now, zoom out with me for one last sweep. Desert reds that happen only when manganese threads the needle. Neon mines where darkness reveals the truth. Spaceborne sparks hiding in crater dust. Quiet blocks from Maine that sync the clocks we live by. Gold masked as telluride until heat breaks the spell. Alpine pastels grown in a peralkaline kitchen. Green spogamine that flips its color with a twist. And a deceiver that looks like quartz and isn't. Which stole your imagination? Which mineral would you chase in real life? The UV glow, the cosmic grain, the pocket that tests your patience, or the rock that tricks your eye? Your shortlist says a lot about the kind of treasure hunter you are.